Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and I'm getting back to a series I was making exploring field programmable analog arrays based on floating gate technology pioneered by my colleague Jennifer Hasler at Georgia Tech. So in macOS, I'm going to double-click on rasptools startup.command. This is a partially done and fairly buggy port that I'm working on, taking the tools that Dr. Hasler's group has developed that were originally written for the Ubuntu operating system that people generally use in a virtual image via VirtualBox. So I'm going to load an XCOS diagram I created called Aaron Voltage Divider. And this is essentially like your standard resistor divider used to drop down a voltage, except it uses two operational transconductance amplifiers instead of two resistors. And you may wonder, why in the world would you want to do that? Well, basically, in your standard world of designing things on a PCB, transistors are expensive and resistors are cheap. But on a chip, like this field programmable analog array that we're looking at, resistors are actually fairly bulky, complicated things, whereas transistors are essentially free. So you'll see people trying to avoid using resistors and using transistors instead. And that takes a while to get used to. So I'll talk about the details about how this voltage divider works in a little bit, but first I want to give you an overview of this XCOS diagram. So you'll see there are some triangles coming out and going into a block. Those triangles are the basic standard XCOS data flow representing outputs and inputs. The squares are a little bit different. Those are implicit nodes that are associated with the Modelica solver software that Scilab includes. I want to test the input and output relationship of this voltage divider, and for that I'm going to generate a ramp signal. It starts at time 0.01 and has an initial value of 0.01. And I'm doing this because all of the examples that came with the Ubuntu image with this tool set don't start at 0. I don't know why, but I figure I'll stay consistent with that. Anyway, this has just a slope of 1. Notice there's nothing here to indicate the length of the simulation. So the final point of the ramp is going to be determined by the simulation time. And actually, I should move my window up so you can see the menus. One moment. Okay, there we go. So I'm going to go up to simulation and ask for the setup. And notice I have it running for 2.5 seconds, I guess. So with a ramp of 1, this input is going to ramp from 0 to 2.5. I'm doing that because the FPAA that we're looking at seems to use 2.5 volts as its positive voltage rail. So this plus minus here is a voltage source, and in particular, it's designed to take the generic XCOS data flow information indicated by the lines connected by these triangles and turn that into a voltage source in the implicit solver Modelica space. So the positive terminal here is this black square over here. The negative terminal is this white square. And notice I have that hooked to ground, again, in the Modelica universe. Now, what I want to do is I want to plot the output voltage here relative to the input voltage. In order to do that, I'm going to use an XY plotting mechanism, which is like the XY setting on an oscilloscope. This is generic XCOS kind of data. Notice it's triangles. So I need a way to turn the square kind of data that we have here, the square terminal data, the Modelica data, back into standard XCOS data. And for that, we use one of these voltage measurement devices. Now, I'm going to do something a little sneaky in that I'm going to imagine that our signals are going to be centered around 1.25 volts because our voltage rails go from 0 volts to 2.5 volts. So what I'm going to do is the negative terminal of this voltage source, I'm going to include a 1.25 voltage source on the way to ground. Why did it do that? That was really annoying. Let me Control-Z that. If I just look at this, click OK, it reset it. No, I want it to be rotated back that way. That was very odd. XCOS is a little quirky. Anyway, notice it presents the 1.25 volts as 1250 millivolts. That seems an odd way of presenting it out here, but that's what it's doing. Anyway, I have one of these voltage mechanisms for the input and another voltage mechanism for the output, both reference to that 1.25 volts. So if the voltages here are 1.25 volts, that then is going to show up as 0 on the scope. And I did that just so my plots are all centered at 0. I found that an easier way to interpret the input-output transfer function. Here I mean just the nonlinearity of whatever this function is, the memoryless nonlinearity. I'm not talking about transfer function in terms of a Laplace domain function. The red line here is special. That's indicating a clock signal. Notice the ramp is starting at an initial value of 0.01. So we're also initializing the clock to start at 0.01 with a 0.01 period. And that's what's driving the scope here. And that's sort of driving the timing of the visualization of the simulation. Let's go take a look at the XCOS Palette to get a sense of where you can find these things. So I'm going to go to View and ask for the Palette browser. Actually, it was already being shown, but it was on my other screen, so I need to move it over from the other screen. There it is. Anyway, most of the things on this chart here are built into the standard Scilab/XCOS. The electrical palette contains the controlled voltage source that we've already seen, along with the constant voltage source and the ground, as well as the voltage sensor. Now, the only thing we have on the diagram that doesn't come standard with Scilab are these OTA blocks. To see those, we have to go down into the FPAA category. And here we can click on Modelica blocks, and we'll see that we have the OTA block, that's OTA mod for Modelica. FGOTA is a special version of that. That includes some floating gate transistors. We have PMOS and NMOS transistors as well, and some other things. And this OTA mod, as well as these other Modelica blocks, these can't be compiled onto the actual physical FPAA. These are only for simulation. If we go up to here to the level 2 circuit blocks, we can find PFETs and NFETs and an OTA, and there's also a floating gate OTA. And these are standard XCOS blocks, not part of Modelica, and these can actually be compiled down onto the hardware. Going back to the stock XCOS blocks, if we take a look at sinks, we can find the XY scope that we're using, as well as other kinds of oscilloscope sort of things. We also have sources, such as the ramp function that we used, and the clock that's driving the scope. Okay, so what's going on with these two OTAs? Notice I have the input going into the positive terminal of the first operational transconductance amplifier, and then I have the output of that going into the negative terminal of the second operational transconductance amplifier, and both of these have negative feedback loops from the output back to the input. Now, for the second OTA, if I had a bipolar power supply, I would just have this positive terminal going to ground. But here, I'm going to have it go to 1.25 volts because that's how I'm referencing everything. It's kind of like guitar pedals generally run off of a 9-volt battery or a 9-volt power source in general. So internal to the pedal, it uses 4.5 volts as its effective ground inside the pedal. Okay, so what's really going on with these two OTAs? Why do we have these feedback loops? So in my class on analog circuits for music synthesis, I have a lecture called Single Pole OTAC Filters, where I derive the idea of an OTAC filter by taking a standard RC filter and replacing the resistor with an OTA. The idea is that the resistor basically looks at the voltages at its terminals and kind of turns that into a current, sort of philosophically speaking, and the OTA does the same thing. So you could replace the resistor with an OTA, with this kind of feedback configuration. So let's fade to black and go Khan Academy style for a bit. So I'll draw my bog standard resistive divider with my resistance R1 and my resistance R2, and we'll have voltages Vin and Vout. All right, so Vout by my standard voltage division rule is going to be Vn times R2 over R1 plus R2. So if I replace R1 with an OTA, I can take the positive input and apply Vi to it, and then put in a negative feedback loop. So I'm basically applying VO to the negative terminal. And the OTA here is now going to create an output current that matches the current flowing here. Let me emphasize that this is an OTA by putting another pin here that represents the bias current that controls GM, the transconductance gain of the OTA. Notice I'm using a standard op-amp symbol with just this variation. That's closer to the notation that Jennifer Hasler and her colleagues use. Other books with OTAs in them will tend to use a notation like this with sort of these two little circles here on the outside, or they'll sometimes use this kind of, I guess it's a trapezoid where the end has been chopped off. But I'm going to here stick with the notation that Professor Hasler uses. Oh, and I should mention that for this all to work out, we need the transconductance gain of the OTA to equal 1 over the resistance R1. Similarly, I'm about to write another OTA, and it might not surprise you to know that the transconductance gain for it, which I'm going to denote G sub M2, needs to be 1 over the second resistance. All right. With that in mind, let me replace the second resistor with an OTA. So for this, we'll take the negative terminal and feed that back up here. It's connecting to Vout. And basically, we'll take this ground here and set it to the positive terminal of the second OTA. That's flowing out this direction that matches the current flowing here. So we could write VO is equal to VI times 1 over GM2 over 1 over GM1 plus 1 over GM2. And simplifying this out, I can multiply the numerator and the denominator by GM1 times GM2, which would give me GM1 over GM2 plus GM1, which I can just swap and write that as GM1 plus GM2. So let's see what that looks like in the simulation. If I click on the RASP design window over here, it will make a set of RASP tool menu items appear. One of them includes docs, block library information. Let's see, we have a whole bunch of blocks here, and one of them is a macro model kind of thing for a voltage divider. So this is for compiling down onto the FPAA itself, but I figure I could use some of the values here as a starting point for our voltage divider that we're building with the Modelica blocks. And let's see, 2 microamps is the bias current for both of the OTAs. So let's go into here. I'll set the bias current for the first OTA to 2 microamps, and I'll set it for the second OTA 2 microamps, and I actually made a text box appear. Let me make that go away. Also notice that in the scope plot here, I set the Xmin Xmax and Ymin Ymax to minus 1.25 to 1.25 volts, because that covers that 0 to 2.5 volt range with everything centered around 0. So I'm taking that 1.25 volts that's in the circuit and interpreting that as my ground reference, basically. Okay, finally, some 14 minutes in, let's hit the simulate button. Let's see, it tells us something about Modelica. You might have reason to go in and look at this temporary directory. Basically, it takes the Modelica and it turns it into a C file that gets run, and the simulation is in progress. So let's cross our fingers. Okay, full disclosure, that attempt to run the simulation caused Scilab to hang. It got stuck on simulation in progress. So I just restarted the RASP tools, and I'm going to try this again. And let's see. Oh, it indeed produced a graph. Here's the results of our simulation. Ah, look at this. So we have this nice linear region in the middle here, as we would expect from our voltage divider. Now, OTAs are not linear devices. When you start to push them to their extremes, they have this hyperbolic tangent kind of nonlinearity. That's true for BJT-based OTAs, like we're used to in most synthesizer designs, and also in MOSFET-based OTAs, like in these FPAAs. You get a hyperbolic tangent nonlinearity if you have MOSFETs that are operating in the subthreshold region, which a lot of textbooks will just call off, but it's actually a useful region to work in. And you get a hyperbolic tangent-like nonlinearity. It's not exactly a hyperbolic tangent if you have the MOSFETs operating above threshold. Anyway, if I zoom in on the graph a little bit, we see that we have a nice region for inputs between around minus 0.5 volts and 0.5 volts. Again, this is relative to a 0. In the actual circuit, things are biased around 1.25 volts. So this is nice. We have sort of a 1 volt peak-to-peak input in which this circuit works. And let's check the various values. So around, say, negative 0.4, I have an output of somewhere around negative 0.2. Around 0.4, I have an output of somewhere around 0.2. So setting the biases of the OTAs, the current biases, and equivalently the transconductances to be the same, I get a voltage divider that divides the voltage by a half, just as if I had equal resistors. So that's beautiful. So let's see what happens if I take the second OTA and reduce its bias current to 1 microamp while leaving the first at 2 microamps. So running the simulation here, I wind up with a graph that's very interesting. It's now a lot more linear throughout the range. And if I take this to the extreme, and I were to say, drop this down to 0 current for the bias. Okay, full disclosure again, it didn't hang that time. It ran the simulation. It just didn't produce a graph. So I restarted, reloaded. Let's try this again. And that time it's happily producing a graph. And now I just have pure happy unity gain all the way through. And that makes sense if we interpret our original circuit. What happens if I set the bias current of this OTA to 0? Well, I guess I really should put a little pin in here to indicate that this is an OTA and not an op-amp. Sorry about that. Anyway, that means that this is not generating any current. It essentially takes that OTA out of the circuit. That's equivalent to taking this resistor out of the circuit. So I have my input voltage and my output voltage just attached by this resistor here. And if the circuit isn't loaded down, well, there's no current being lost across that resistor. So, hence, unity gain, with gain in quotes. Now, there is an important distinction between this resistor setup and this OTA setup in that there's current flowing all the way through the resistor. So the current here on the right side of R1 is matched by a current flowing into the left side of R1. And the current flowing through the top of R2 is matched by a current flowing through the bottom of R2. But there's no equivalent on the OTA side. There's no current flowing through here. So what that means is that in addition to being a voltage divider, if you want to use this that way, i.e. if you're setting the bias current here to something that's not 0, it's also a buffer. So the input here is buffered from whatever is out on the other side. And that's the case if you have a BJT-based OTA, but those do have non-perfect input impedances. But MOSFETs have extremely high input impedances. So this is a very, 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 very good buffer. In fact, if we wanted to, we could just take this part out altogether, and this would not be a great buffer because obviously there's a current flowing through here. But over here on the right, if we take this out altogether, well, this just looks like a voltage buffer effectively if I'm not connecting anything over on this side. Now, of course, if I load this down, something will happen. But if I were to take the gain here and crank it up, that's equivalent to taking this resistance and cranking it down. So I can pretty much use this as a voltage buffer if I'm willing to take the gain and make it very high. If I go back to my RASP design menu to make the docs menu appear again, I can get that block library information again. Let's see, OTA buffer, that's what I was looking for. So this is that kind of structure. We have an OTA. We have the bias current set all the way up to 10 microamps, so that's even 5 times that 2 microamps that I had in the simulations. And you take the output, hook it to the negative input, and there's your buffer. Now, the weird thing about that is you're used to using op amps that look like this as voltage buffers. Here we're using an OTA, and the reason we're using OTAs is these are prevalent on the FPAA.